All right, folks, welcome to this video. Today we're talking about exponents, we're talking about logs. I wish I could be there in person with you, but we're gonna have to make do with this. Again, for this topic, I understand that logs might not be the most familiar. So my goal for this bootcamp portion is just, here are your logarithm laws. We're not going to talk tons about the log function right now, but I need you to have a baseline understanding of how to convert between an exponential form and logarithmic form in an equation, and have a base understanding of how to expand and condense certain log functions or log equations or log expressions. Okay, so know that I'm not expecting you to leave this video a complete expert. I want to give you some laws. You can trust these laws, you can follow these laws, and I want you to be able to apply them. Okay, so that's my goal. Let's run through these. The exponent ones, you have dealt with these ones before. So if I have x to the power of a times x to the power of b, how would you consolidate that? Like, how would you solve that? Hopefully you're saying or thinking, I would just need to add those exponents. Okay, so your example of this would be, I have x squared times x to the third. That would end up just equaling x to the fifth. I added 2 plus 3. Another law for us, if you have x to the power of a over x to the b, to simplify that, you would just have to subtract. Let me go back there. You would have x to the a minus b. Okay, so your example of that, I have x to the 7th over x to the 4th, and that would just simplify down to x to the 3rd. All right, we're going to keep grooving with this. Again, these exponent laws, I know you've dealt with these ones before. It's the log ones that might be a little fresher for us. If I have x to the a and all that's raised to the power of b, you guessed it, I just need to multiply those exponents. Our little example, wow, that's supposed to be an arrow, yikes. Our little example here would be x squared and then raise that to the power of 3. That's going to give us x to the 6th. I have a few more for you. If you ever have a negative exponent, I can rewrite that as 1 over x to the positive a, okay? So for instance, our little example here, if I have x to the negative 3rd, I can rewrite that as 1 over x to the 3rd, all right? All right, last few, we're going to try to squeeze them in here. If you ever see anything raised to the 0th power, that's going to equal 1. And if you ever have anything raised to the 1, it's just going to equal itself right there, okay? Oh, I'm realizing I forgot one. Can I add another one down here? If you ever see x to the a over b, so like a fraction form, you can actually rewrite that as a radical. You can pull that b outside. That's the bth root of x to the a, okay? That one's going to come in handy for you on a few of the delta math ones, maybe. And we will be using stuff like that. Like in calc problems, you might need to rewrite stuff like that. And I'm just refreshing us on it now. So by the time we get to that, that's just going to be a little blip and we can focus more on the actual calculus, okay? So those are your exponential laws. Your log laws are a little bit different. So a log is just a type of function. You can kind of think of it as like something you're doing to a number, doing to a function. So if you ever see something like this, log of a times b, you can separate that actually into log of a. And again, a and b are just representing numbers here, plus log of b, okay? So for instance, I see log of 2x. I'm allowed to write that as log of 2 plus log of x. If you ever just see a log like this without any small subscript numbers, which are called bases in this case, then picture an imaginary 10. Okay, so if you just see log, it would be log base 10. On delta math, you'll have some problems where you see like log base 2, log base 47, different numbers there. But here, I don't see any number right here. So it just means there's a hidden little 10 there. That's what would normally go there. Okay, and you'll see what I mean when we switch back and forth between these two forms in a second. Another rule for us, or law, if you ever have log of a divided by b, I can rewrite that as, oops, sometimes the pencil stops working, log a minus log b. You can kind of see some similarities with these in the exponential form, but it looks a little different. So for instance, if I have log of 4 divided by 5, I can rewrite that as log of 4 minus log of 5. All right, let's keep going. If you have log, pencil stopped working again, log of a raised to the b, you can take that exponent and put it in front. This one's a little weird, so I can rewrite this as b times log of a. Okay, so for instance, I have log of x to the 4th. That would become 4 log x. Okay, a little bit of a weird one. If you ever see something like this, log with this little subscript, that's your base x of 1 over x to the a, that's going to equal negative a. Okay, I'm going to let that one sit there. And a few of these other ones, I'm going to let them sit there. In a second, I'm going to show you how to convert between these forms. So for right now, just let this sit here. But keep in mind what you know about negative exponents, right? Keep this over here in mind. This is playing a role somehow with this, okay? So we'll see that a little bit more in a second. Okay, a few more rules here. If you ever see something that looks like this, log base x 1 equals 0. Ooh, that should link with this rule over here. Cool. And if you ever see log base x of x to the a, that's just going to equal a. If you ever see natural log of 1, that equals 0. If you ever see natural log of e, that equals 1. Natural log is just a special type of log with a base e. E represents a constant number, 2.72, blah, 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 blah. So natural log, we just simplify it, right? ln. Pretty sure it comes from Latin. Oh, now it's going to bother me. I have to look that up and make sure what that comes from. But ln stands for natural log, and that just has a special base of e, that number right there. Okay, so here's how you convert back and forth between forms. If you ever see something in this format, I'm going to use some fun colors here. I'm going to put a B for base. I'm going to put an A for answer. And I'm going to put an E for exponent. If you ever see this, I call it log bay, base, answer, exponent. I can rearrange this and write it in exponential form as base raised to the exponent equals my answer. Okay, so you may always convert back and forth. If you see either one of these forms, you can convert from exponential form into log form. You can convert from log form into your exponential form. Okay, so again, just keep in mind log bay, B for base, E for exponent, A for answer. All right, we'll deal with this in a couple of problems. So let's put these laws to use. Again, I know I'm not explaining tons of like the why, the how, the blah, blah, blah. But I want us to have these laws, baseline knowledge of the laws, and then how can I use them? If we have time more in this class, we'll be able to get more into logs, but it is what it is. Okay, I also want to just show you, like, for instance, this one over here. If you were to rewrite this equation, you would have base x raised to the a equals answer x to the a. Cool, that works out, okay? Same thing with this. If you were to write base raised to the exponent equals answer. Cool, okay, that works out. So you see I'm just taking each of these base, exponent, answer, and I'm plugging them in. I'm converting between forms. Hopefully you can kind of see how these rules are working together, these laws are working together. Okay, that's a lot of circles, that's a lot of writing. I'm going to take some of that away, and we're going to move into our next problem. Okay, let's move on to talk about expanding log expressions. So what we mean by this is we're going to start with some pretty packed expressions, actually. So something, for instance, like this, log base 3 radical xy. We're going to start with that one, okay? In order to expand a log expression, you want to break it up as much as possible. So the first thing I would do here is I would actually rewrite that radical as a fractional exponent. So I have log base 3 and then xy raised to the 1/2 power. That's one of your exponential rules, right? I can rewrite a radical as a fractional exponent. And then what I'm going to do is I'm going to use that rule that says if you have log of something raised to an exponent, you can pull that exponent out in front. So this would then become 1/2 log base 3 of x times y. We had a rule for logs that said if I have the log of two things multiplied, I'm allowed to split those up. So your final form here would be 1/2 log base 3x plus log base 3y. And yes, you do need to include the base for each of those, okay? So just for this particular problem, we had a base of 3. You need to make sure that you have that base of 3 with both the log x and the log y. Okay, if you wanted to, you could go ahead and distribute that 1/2, but I would accept this answer just the way it is, 1/2, and then in parentheses, the log base 3x, log base 3y, okay? So that's our first example of expanding. You start with something kind of crunched together with just one log, and you expand it as far as you possibly can. Our next one, I'm going to use natural log, which again has that secret base e, and this is xy squared divided by z. Okay, so the first thing I see is this division right here. Well, one of our log rules said that if you have things that are being divided, and I'm going to actually rewrite this like this. Natural log of xy squared over z, then you are allowed to rewrite this as the natural log of xy squared minus the natural log, oh, that's just an h, the natural log of z. Okay, natural log of z, I can't do anything else. That's just going to stay where it is. But over here, I could keep expanding. I see x and y squared are multiplied, so I'm going to split that up into ln x plus ln y squared minus ln z, natural log of z. There's one more thing I can do here. Any guesses as to what it is to expand this a little bit more? It would be to pull down that exponent. So I'm going to write this as my final answer. Pull down that 2, natural log of y minus natural log of z, and that would be your fully expanded form. Okay, so we're just using the laws to go from one log, any base, could be natural log, into try to separate this and split it up as much as possible. Similarly, we can condense logs. So this is the example we're going to do here. 2 log of x plus log y minus 1/2 log, pencil stopped working, log z. So here we're just working backwards. I'm starting with a bunch of different log terms, and I want to end with just one of them, okay? So the first thing I'm going to do here is say, hey, I see these numbers out in front. I want to use that kind of exponent log rule and put them as exponents. So I'm going to do that for this 1/2, and I'm going to do that for this 2. So then I'd have log x squared plus log y minus log z to the 1/2. If I see 2 separate logs being added, well, I could rewrite that as log of x squared times y. And then if I see 2 separate things being subtracted, I could write this as log x squared y over z to the 1/2. How could you rewrite z to the 1/2 without a fractional exponent? It would end up just being radical z. Okay, remember, fractional exponents you can always convert into a radical. Keep the numerator with the numerator, so 1 is kind of secretly with z. Take that denominator and make that your root. Okay, so square root, I don't have to actually write the 2 out there, but you can kind of see what's happening there. Okay, you should be able to plug logs directly into your calculators. If any of you have an issue plugging in something, for instance, like log base 3 of 10, or that might be a terrible example, but let me know if you can find the way to plug in a different base into your calculator. If you can't, that's something that we can chat about tomorrow. There's this formula that you can use, but I'm quite sure for most of you, you'll be able to just plug them in your calculators. But check that a second. If you need to, you can always Google how to plug in log with a base into, and then type in the name of your calculator. Okay, last thing we need to chat about in this video is solving log and exponent equations. And y'all, if you're getting this, I hope that you put me on 2 times speed. That's allowed. If you're not getting this, slow me down. Stop the video. Do what you need to do. Okay, we're going to solve a couple of equations. We're going to start with this one. Log base 5 of x equals 3. Just looking at this, I would not expect you to solve this. What I would expect from you is rewrite it as an exponential equation and then solve the exponential equation. That's a lot easier. So remember, log bay, 5 would be your base. Your exponent would be this 3, 5 to the 3rd equals your answer. x. And when I say answer, I'm using that as filler for like the thing on the other side of the equation, okay? So to solve this out, x is just 5 cubed, which is 125. Okay. Try another one. Log base b 1 equals x. Okay, this is weird because I have a b and an x. Let's convert forms. Base to the exponent equals answer. What would x absolutely have to be for some base raised to x to equal 1? Well, the only time that's going to equal 1 is when x equals 0. It literally doesn't even matter what b is. Anytime you have some base raised to 0, overall it will equal 1. All right, one more. Log base x 25 equals 2. Convert forms over here. Base raised to the exponent equals your answer. This one you can solve it or you could just look at it. Either way, if I were to actually solve this, I would want to get rid of that square. So I'm going to take the square root. Over here I have x. Over here I would have 5. And for this one, some of you might argue, well, wouldn't it be plus or minus 5? When you're dealing with logs, you're only going to be able to get positive. So only positive because logs may only have positive bases. And you can see this in the graph. Like if you were to actually plug this whole thing into Desmos, you'll see your log, your x value is not going to be able to be anything negative, okay? All right, I want us to do one different type of problem. You'll see stuff like this pop up in Delta Math. Am I going to be strictly testing you on this tomorrow? I might throw one of these on, but this, honestly, I've seen this show up in SAT problems and ACT problems. They're just helpful ones to know. I think they're kind of fun. So to close this section off, we're going to do this problem. It's a little more complicated, but I think it's kind of fun. I have 3 raised to the x squared plus 4x. All of that is the exponent equals 1 over 27. How would we solve this equation? At first, it looks a little bit daunting. When you see something like this, your main goal is how can I rewrite both sides of my equation so that they have the same base? I'm going to leave this side alone for right now, but is there any way that I could rewrite 1 over 27 as something with a base of 3 and then figure out what exponent to raise that to? I think the first thing I'm going to do over here is say, well, 27 is the same as 3 cubed, right? I don't really love that it's in the denominator. How could you rewrite that? Think back to your exponent rules. If I see some kind of exponential expression in my denominator, I can always write that as a negative exponent. Okay, so what we've done here is we've said I'm going to leave my left side alone. My right side I'm going to rewrite as 3 to the negative third. Perfectly legal. We just used our exponent rules. Well, now you can see that you have the same base on both sides. For this equation to hold true, your exponents would need to equal each other. So I can rewrite this as x squared plus 4x equals negative 3. At this point, this looks like a quadratic function, excuse me. So I'm going to want to add 3 to both sides. You're going to need to do a little bit of factoring here. Let me move this down a little bit so we can see. X squared plus 4x plus 3 equals 0. When you factor this, we are looking for a pair of numbers that adds to 4 and multiplies to 3. I think positive 1 and positive 3 would work out for us. So that means your two answers for this overall equation would be negative 1 and negative 3. Okay, and you can test it out if you want. You can plug them back into your original equation. Do they work? Check it out. Those are your two answers that you would be getting. Again, you'll see this show up on Delta Math a handful of times. Otherwise, I don't know. I think these ones are fun, trying to figure out the same base and going from there. And like I said, I've seen these on SATs and ACTs here and there, but now that you know how to do them, that's a nice, easy point for you, right? Okay, I'm going to stop the video there. You'll have another video from me about composite functions. And with that, you should be good to go. Congratulations.